Club heartily welcomes you to yet another electrifying session, this time on quantum information theory. We are absolutely delighted to have Maria Violaris with us today to kickstart our guest speaker series of Jontro Tontro 2022, the annual Tech Fest of JUSC under the Women in STEM banner. Maria, besides being a PhD student in quantum information at the renowned Oxford University, is a prolific academician and excellent communicator of science, and has been decoding the mysteries of quantum theory through her consistent contents and eloquent speeches. She is also the founder of Oxford University Quantum Information Society and is currently a quantum computing intern at IBM. So instead of doing a shoddy job of summarizing her brilliant academic profile, let's hear all about it from Maria herself. So over to you, Maria. Welcome to Jadavpur University Science Club.
Great, thank you for the introduction and thanks for inviting me to give a talk. I'll share my screen so you can see the slides. I'll just find it. Okay, so you should be able to see my screen now, is that right? Can you see it?
Yeah, we can see your screen.
Okay, so you can see the slide.
Yes, we can see.
Okay, great. So I'll start the slideshow. Okay, so if everything's okay, I'll get started.
Yes, you can start it.
Great. Well, yeah, as I said, thank you for inviting me to give a talk. So I thought I'd focus on one of my favorite aspects of quantum science and technology, which is quantum thought experiments. And I've called this talk Testing Time, Tech, and Too Many Cats Inside Your Head, because I'm going to talk a bit about some thought experiments that link to each of those three things. So yeah, I'm hoping by thinking about quantum thought experiments, we can think about the really strange aspects of quantum mechanics that make people really interested in the science behind it, and also the technological aspects that lots of companies and researchers and universities are also really interested in exploring to try and push forward our technology. So I'll start by just summarizing a bit about my background and the kinds of things that I've done in the quantum area. Then I'll explain a few of these quantum thought experiments. And at the end, I've also just put a slide with some resources in case you want to look into quantum information more yourself. So just to start with, I kind of became interested in physics when I was around 15, towards the end of high school. And I think I became interested in physics, not really because of the topics we were learning at school, but more because I started reading about different interesting things like particle physics and quantum physics, and found out that there's this whole model about particles where protons and neutrons in atoms are made of quarks, and the quarks all have these strange names like up, down, top, bottom, charm, and strange. And yeah, I thought that was really interesting. And I ended up kind of making this little cartoon video for a competition, which didn't win anything in the competition, but it was fun to do and to make some cartoon particle physics characters. And then I went to do my physics degree at Oxford, and then I stayed there to do a PhD. And as was mentioned earlier, I started Oxford Quantum Information Society. And then, so last year I gave a talk for the society about my research and about a project linking to the quantum arrow of time, where I have put a screenshot here from the talk, which I explained using eggs. So you can check that out if you're interested in the direction of time. That won't be what I'm talking about today. And alongside that, I really like outreach and things like working with younger students or trying to encourage people to think about quantum. So at the moment, I'm helping run this quantum video competition for high school students in the UK. And it'll be really cool for more places to do that as well. So if you're ever interested in running something like a competition, you could do something similar with a video competition in your region. And last summer I did an internship at a quantum software company called Riverlane, which is building software for quantum computers. And so quantum computers, you may have heard about them a bit in the news, but the idea is that for certain problems, they could be able to solve them much faster, like simulating chemicals for medicines, for medical drugs. So I did a project with Riverlane, and I was using like Raspberry Pis and circuit boards to create a kind of model quantum computing lab, using the Raspberry Pis. And so it was just a kind of simulation of a real lab. And then, recently I've been doing an internship with IBM Quantum, and I am making some videos about quantum paradoxes. And my first one was about the quantum bomb tester. And I've recently put that on YouTube, and I'll talk a bit about the bomb tester a bit more later as well. So that's a summary of my background. And then, I've mentioned a few times that I'm interested in thought experiments. So I thought a good place to start is to think about what a thought experiment actually is. So I think of a thought experiment as when you imagine a scenario and then think about what happens in that situation. So I've just put some pictures of like fantasy lands here that I found online, because I think the idea with thought experiments is that you don't have to think of something that you could literally do in a lab right now. It can kind of push the boundaries of what's possible, and you imagine what would happen in this hypothetical situation. So that's what I think of thought experiments as, imagining a situation where things are happening. And a while ago, I wrote an article about thought experiments, and I started it by saying that a pioneer of thought experiments is Galileo, who is famous for lots of important discoveries, and he used thought experiments a lot. And one of the things he used thought experiments for was to work out, to be able to explain how the Earth can be spinning on its axis, which causes the day and the night, but we don't feel the Earth moving, because people thought, how can the Earth be spinning so fast if I don't feel it moving? And he used thought experiments to explain that. But then somebody said, in response to my article, they said, oh, I think they wrote into the magazine where I published it, and they said, you should have turned back the clock more and considered the ancient philosopher Democritus, who used thought experiments to come up with the idea of an atom by thinking about what happens if you keep splitting an object more and more until it's, what's the smallest possible object you can get if you keep dividing it. So thought experiments have, been right from the ancient times, and more recently, Einstein is famous for his thought experiments. He imagined kind of what would happen if you sat on a photon and tried to move as fast as the speed of light. That helped him think about his famous theory of special relativity. And he also used thought experiments to think about gravity and general relativity, because he realized that if, say we're now on the Earth, and if the sun just instantly disappeared, it would have to take some time for us to notice, for the Earth to notice that the gravitational pull from the sun had disappeared. It can't happen straight away. And by thinking about that, he realized there was a problem with our explanations for gravity. So thought experiments have been very fundamental in the history of science. But and I just summarized here some of the reasons why I find thought experiments really useful. Some of them can be a very kind of simple situation, like Einstein imagining, what happens if the sun disappears. Then it's not a complicated situation, but it has very big, profound implications, because it means our theory of gravity is completely wrong. So it can be a simple thought which leads to big consequences. Some thought experiments are very puzzling, and physicists and other scientists are still debate them. There are some that last for years and years with no one really knowing what the answer is, or they work out the solution to a paradox in the thought experiment, and then it changes years later when people discover something else. They also are useful for putting science into a story, because you can say, well, imagine this situation, instead of just explaining some science. And they're good for organizing different aspects of information about a problem into kind of one story. And the final one of suspend reality is the idea that thought experiments, unlike real experiments where we're limited by what we can do and by our current technology, with thought experiments we can imagine we're in the best lab in the world. You can be anywhere in the world, and you can imagine that you've got this perfect technology. You don't need to worry about approximations and things. So it kind of lets you enter this world of experimenting with perfect things in your mind. So now I'd like to get on to talk about some quantum thought experiments. So I'll talk about these three sections: time, tech, and too many cats, just to give an idea of what some quantum thought experiments look like. So I'll start with one about time. So there is a thought experiment called the delayed choice quantum eraser, which the physicist John Wheeler kind of discussed it. I think it was discussed by some other people before him as well, but he's become known for this thought experiment. And it seems from this that if we make a measurement now, it could affect something that happened in the past, like something that happened, it could have happened 5 minutes ago or years ago, but something we do now seems to be able to affect the past. And lots of scientists would disagree that this can never be possible, and so this has caused a lot of discussion since it was proposed. So let me explain the general idea. If you've ever kind of watched some introductory videos about quantum physics, you might have heard about the double slit experiment. So I'll just summarize it here, because this quantum eraser thought experiment is like an extension of this. So with the double slit, the idea is that we start with a particle, so it could be, say, a photon, a particle of light, and we send it through to a kind of screen which has two slits in it. And then what happens when the particle goes through is that it part of it goes through one of the slits, and it also kind of goes through the other slit. If you imagine like a wave coming through, and then these two gaps, and then these two areas where it came through the slits kind of overlap, so that at some points they reinforce each other and make a bigger intensity of the light, and at other points they cancel each other out, and then you get these low intensity areas. So we end up with this pattern when you so we send like a particle of light through this double slit, and then we see where it lands on the screen, and then we do it again and again. And every time you do it, the particle has these interactions with itself, which we call interference, where it leads to some parts having high intensity, some parts low. So when you send the particle through, lots of particles through, you end up with this pattern on the screen. And so the idea of this experiment is that it shows that these particles behave like waves, because they can have parts that they can interfere with each other to add up to make high intensity bits and cancel out to make low intensity bits. So the other thing that could happen is we could put a detector at one of the slits. So I've represented the detector by a pair of eyes here. And what happens when you look at the slits to see which slit the particle came from? So you check whether your photon, your particle of light, is in one slit or the other. In this case, you don't get the interference between the two sides, between the parts of the photon that went through both slits. It's like the photon only went through one slit or the other slit, which is what a particle would do. And you end up with this pattern where for when you've looked at the photon and it's gone through the top slit, then you have high intensity around that area. And when it's gone through the bottom slit, you have high intensity around the other area, but you don't have this pattern of these places where it's added up to make really big high intensity areas, or cancelled out to make the low intensity areas. So that's the kind of standard double slit experiment, which is meant to show how strange it is that particles can behave as waves or as particles, depending on whether you make this, whether you detect which way they went or not. So, so now let's see what happens when we kind of think about this experiment a different way, which is the delayed choice idea is that what we do is we don't we put our detector there, but then we measure the results of the detection in a way that doesn't give us any information about which slit the particle came through. So our detection was, we still did a detection, but I've represented this by the eyes kind of looking away from the double slits because we get our measurement results in such a way that we don't know which slit the particle went through. So the interesting thing here is that when we do this special type of detection without having the information about which slit the particle went through, we can actually get back an interference pattern where we have these bits where the waves came together and bits where they cancelled out. So we can essentially separate out this pattern into these kind of separate patterns where we can see that there are some parts kind of going up and down rather than just these two peaks. So by not finding out which side of the slit, which slit the light went through, we now have the wave behavior again. So the reason that some people interpreted this as meaning that we can cause a change backwards in time is that it seems that if we choose to do the measurement one, where the detector is checking, we find out which slit the particle went through, then it looks like light chose to behave as a particle in the past before we decided how we were going to get our measurement results out. But if we get our measurement results out with number 2, where we're not getting that information about which slit the particle went through, then it looks like light chose to be like a wave in the past, because we can get this interference pattern where we have the overlaps, which is what we'd expect from a wave. So it seems that we could have made this choice ages after the experiment, and it could somehow affect whether the light was a particle or a wave in the past. So this doesn't really make sense, or that's, I think, the solution to the thought experiment is really that light doesn't behave in a way where it's always either a particle or a wave. It has properties that are like both, and there's nothing wrong with being able to get this pattern where we have the wave behavior when we don't know which slit the particle went through. There's nothing wrong with that. Like, light can have at the same time show these two patterns without having to have kind of chosen to be a particle or a wave in the past. So I think the best way to summarize it is that with the first choice, we know which way the light went, and we can't see the interference pattern. So that's the kind of particle style behavior. And in the second choice, we don't know which way the light went, but we can see this interference pattern, which we think of as wave-like behavior. And there's nothing wrong with these choices, with us being able to make these choices. So the conclusion is that, I don't know if you'll think this is the more exciting or the less exciting answer, but no, a measurement now can't affect the past as far as we know. But I think the thought experiment is important because it allows us to have a story where we can think about whether this can happen and what is it that prevents it from happening. And getting this explanation clear is something that's still, there are still recent discussions about this. And yes, it's something that there's a lot of different explanations trying to explain it correctly. So that was the thought experiment about time. So I'll move on to the next one, which is about tech. So this thought experiment is one that I think is really interesting because it really links ideas about the fundamental nature of reality with technology that could transform lots of aspects of our lives and have lots of practical applications. So there's a nice link between the fundamental and practical side in this thought experiment. And it's based around the idea of a universal quantum computer being possible. So this thought experiment is one that was proposed by the quantum physicist David Deutsch, and it was kind of one of the lines of thinking that led him to proposing a universal quantum computer, which is something that a lot of people are working on now, and as I mentioned earlier, could solve certain problems much faster than ordinary classical computers can. And I'd just like to show you this quote I found from an article I was reading, where David Deutsch was kind of discussing this thought experiment. And then after kind of explaining the thought experiment, he says, so I had to postulate that this quantum coherent universal computer, and that was really my first proposal for a quantum computer. So yeah, I thought it was interesting that this this thought experiment led to this proposal in a way. So to understand this thought experiment, first I need to explain what a qubit is. So you might be familiar with bits. So classical computers are based on bits, which can be either a 0 or a 1. And quantum computers are based on quantum bits, which are called qubits. And I think the best way of understanding qubits is using the image of a sphere. And this is kind of technically correct as well, that we can imagine a qubit as the sphere. And at the top of the sphere, the qubit is a 0. And at the bottom of the sphere, it can be a 1. But a qubit can also be at any other point on the sphere, which is a combination of 0 and 1, which we call a superposition of 0 and 1. And so in this picture here, I've got the arrow showing where what state the qubit is in, and it's halfway between 0 and 1, so it's a superposition of 0 and 1. And yeah, the thing with superpositions is that when you measure a qubit in a superposition of 0 and 1, then you get an outcome of 0 or 1 kind of at random, with some probability of 0 and some probability of 1. But if it's halfway between 0 and 1, then your measurement result of 0 or 1 will be completely random between the two. So next I want to introduce this little robot which I've used to represent a quantum artificial intelligence. So it's like a conscious, like a person, but uploaded running on a computer. So it's a digital artificial intelligence that's able to measure things and talk. And yeah, I'm imagining that we have this artificial intelligence here. And then I've also got me here as a observer. So I'm going to be controlling this robot and the qubit to do this thought experiment. So to start with, the quantum AI, the little robot, looks at the qubit and observes its state. So as I said, when it measures it, the robot sees either 0 or 1. And in this case, it sees 0. So the robot sees 0, and then it tells me that it saw a 0. And then what I do is I basically undo everything that happened to the robot and the qubit so that they go back to how they were at the beginning. So the robot doesn't know what it measured, it doesn't even remember that it measured anything, and the qubit is back to the superposition of 0 and 1. And the reason I can do this is because all the laws of quantum physics, they're all symmetric with time. So any laws of quantum physics, you can always reverse them. And so because I've got my quantum AI robot and qubit that have just interacted using quantum mechanics, then I can reverse everything so that it's back how it was before. But I remember that the robot told me that he saw 0. So I undo everything, and then I repeat. So we do this experiment again. So the robot measures the qubit again. It tells me what it got, and then I reverse it so that it doesn't remember anything, and the qubit goes back to its superposition. So after I do this lots of times, there's 2 possibilities. What we'd expect to happen if everything was correctly described by quantum mechanics, if I managed to reverse everything properly, then every time the robot measures the qubit, it should get either 0 or 1, one of them about half the time. So we should end up with a mix of 0 and 1. But some people think that when you measure a qubit, it collapses, the superposition collapses into either a 0 or a 1, and you can't undo that collapse. Like it just collapses into 0 or 1, and we can't reverse that. So if that was true, then the qubit would have to be 0 every time, because it collapsed to 0 the first time. So when we do it again and again, it must stay 0 because it can't undo that collapse. So, so this thought experiment was proposed to essentially test out or provide like a theoretical situation where we could test out whether qubits collapse when you measure them or whether they don't collapse when you measure them. So this is, something quite fundamental, because you might have heard about these different interpretations of quantum mechanics. There's the Copenhagen interpretation, which says that when you measure a quantum system in a superposition, it collapses to one state or the other. Or there's other interpretations like the many worlds interpretation, which says that there's no collapse. You just become correlated with the thing you're measuring. And some people might say, oh, well, we can never test whether... so in this many worlds interpretation, they'd say that both the 0 measurement and the 1 measurement happen when you measure a qubit. And so it's kind of many worlds because you have both situations happening. And yeah, this would be a way of testing that a difference between the situations where you have the collapse and the no collapse. So how did this link to a quantum computer? Essentially, when David Deutsch was thinking about this, he thought, well, the robot with the qubit, like what kind of machine would this quantum AI be able to run on? And it would have to be a quantum universal computer that can allow us to control the quantum interactions between things, for example, when the robot measures the qubit, and then have the control to be able to reverse that as well. And so, yeah, this was a kind of the original idea for a quantum computer. So I guess the answer to this one is that maybe a universal quantum computer is possible. We haven't done it experimentally yet, and it would to do this actual thought experiment with the quantum AI is very far into the future to be done experimentally, which is why it's nice to do it with thought experiments, to know that at least in theory we could do this test, even if we don't work out how to actually build a quantum AI for a very long time. So, so that's the tech thought experiment. And finally, I want to talk about too many cats. So I'm going to talk a bit about the quantum Bonn paradox. So this is the one that I discussed for my video with IBM Quantum. And I want to talk about how some people think that it solves the Schrödinger's cat problem. So this is kind of related to the previous thought experiment as well. So you might have heard of the Schrödinger's cat.
I'm actually sorry to interrupt. Actually, we have a question from the audience side, those who are watching in the YouTube. So yes, one question is there that can the power of quantum computing be used to train machine learning models so that more data can be analyzed in shorter period of time for more accurate results? That's the question, ma'am.
Yeah, lots of people are working on quantum machine learning algorithms, and the idea of these is that for certain data sets that have certain properties, a quantum machine learning algorithm might be able to process that data, especially on large scales, more efficiently than a classical computer. So there's lots of research being done on those algorithms, and I think that there's been certain situations where people have proven that there's a quantum advantage for certain machine learning algorithms with a specific type of data set would be able to give a speed up over the best known classical algorithms for that data set. There are other situations where people are just kind of trying things out. So it looks like quantum might help over classical, but they don't know for sure, and they haven't checked. Like, people could come up with better classical machine learning algorithms that then are even better than the quantum ones we've thought of. And so there's constantly kind of people working on both sides of pushing forward those two things. But it's definitely an area that people are looking at in research and in industry, and quantum computing companies are looking into that as well.
Okay, thank you, ma'am. Ma'am, we have one more question.
Yeah.
Ma'am, we have actually one more question from the audience side.
Mm-hmm.
Okay, ma'am. So why are qubits revolutionary in the field of information storage and processing?
Why are qubits revolutionary? Is that the question?
In the field of information storage and processing.
Mm-hmm. Yeah. So I think you can think of the role of qubits as being very similar to the role of bits for classical technology. So classical technology is all based on classical information processing technology is all based on everything being encoded in ones and zeros, and then kind of these higher and higher levels of being able to manipulate those until you have kind of programming languages like Python that you can type your instructions on a high level. And qubits play a similar role for quantum computers, for example, because your quantum computer will be based on a set of qubits, and you can say right now, a lot of the time when you're coding a quantum computer, you'll kind of code what's happening to those qubits directly. But over time, we should be able to, like with classical computing, get to the higher and higher levels so that you can just type the instructions of what kind of things you want your computer to do, and then it manipulates the qubits for you to perform the task you want. And qubits, they all have this kind of property of being able to be described by the points on the surface of the sphere, but physically they can be made of loads of different things like superconductors, ion traps, and photons. There are loads of different physical implementations of qubits, and they've each got advantages and disadvantages for how good they are for information storage and information processing. So I think that over time, all of them will kind of find their uses and what they're kind of best at. So different physical implementations of qubits are important for those different technologies as well.
Okay, Maria, there's another related question on qubits from the audience. So the question goes that when we measure the qubit, aren't we already fixing one value of the qubit and eliminating the other?
So when we measure a qubit, so if your qubit is in a superposition of 0 and 1, and so let's say you have a qubit in the superposition of 0 and 1, and then you have another qubit which you're going to use to measure the result of the first qubit. Well, then what you want is for your second qubit to be in the state 0 if your first qubit is in the state 0, and you want your second qubit to be in the state 1 if your first qubit was in the state 1. So to make sure that your measurement qubit is going to correctly measure your first qubit, you can let them interact in such a way that they become entangled, which means that when the first qubit shows 0, the second one will show 0, and when the first qubit shows 1, the second one will show 1. But altogether, they're still in an entangled superposition. So they're in a superposition of both qubits saying 0 and both qubits saying 1. So that's how you can think of the measurement of the qubit on like the quantum level, if we're just using qubits to measure qubits. Now, it gets a bit more complicated and controversial when you have like a large detector or a person measuring the result, because then if we use quantum mechanics to model the person as lots of quantum systems, then would also get that when I measure the qubit, I enter an entangled superposition. So then me and the qubit are in a superposition of both of us me having seen the qubit say 0 and me having seen the qubit say 1. But some people think that when I measure a qubit, it somehow causes the qubit to collapse into the 0 or 1 state. So some people think that both the 0 and the 1 are kind of out there, but we can only see one of them. And other people think that the other one actually isn't there once you've done the measurement. So that's a kind of controversial question. But yeah, I mean, what you see in both cases is the same, that if I measure a qubit, I only see one outcome, and I can only know about the other outcome if if kind of before I measure it, I let it do some interference with something else, and then I can see that it was in a superposition of 0 and 1. It wasn't just a 0 or just a 1. Yeah.
Okay, thank you. So you can continue with your presentation now.
Okay. Yeah, thanks for the questions. They're all interesting questions. So I guess this is related to what I was just saying. This is the famous Schrödinger's cat paradox, which is that we essentially have this radioactive atom or material which essentially enters a quantum superposition of having decayed and not decayed. And if it decays, then it causes this hammer to smash poison, which kills the cat. And if it didn't decay, then it doesn't, and the cat stays alive. And if we used quantum mechanics to describe everything here, then the cat would become entangled with the substance that was in a superposition, and so the cat is alive and dead at the same time because it's an entangled superposition of being alive with the substance having not decayed and dead with it having decayed. So this has caused lots of people to discuss what quantum mechanics means for reality. And I want to discuss the quantum bomb paradox, which has some links to this, as you'll see. So the idea of the quantum bomb paradox is that we imagine you have a box and you don't know what's inside. There could either be a bomb inside or it's empty. But this bomb would be sensitive to even a single photon touching it, then it would explode. So classically, there's no way to work out whether there's a bomb in the box without it exploding, because any way you try and detect that bomb, it would explode because it would have to interact with something to be detected. Now, Elitzer and Weidmann are two physicists that proposed a quantum bomb tester, which allows us to work out whether there's a bomb in the box without it exploding, using something called interaction-free measurement, which is incredibly surprising and a really counterintuitive and really unusual aspect of quantum mechanics, with some interesting technological implications as well. So I've kind of made an animation of a setup here, where here we have a photon source. So this is a photon, the particle of light. This is a beam splitter. So when the photon hits a beam splitter, it goes into a superposition of being reflected and being transmitted straight through. These are mirrors. so they'll just reflect the photon. And then it will meet, the two paths of the photon will meet again at the second beam splitter, where they can interfere using their wave-like properties to end up completely at the... so these two are detectors which detect where the photon went. And in this case, they interfere so that the photon only goes to this detector on the right. So what happens is, so we've seen what happens when there's no bomb in this setup. But if there is a bomb, then something different happens. Essentially, when the photon reaches the bomb, it goes into, well, depending on your interpretation of quantum mechanics, it either collapses into the transmitted or reflected state, or it becomes entangled with the bomb into a superposition of having collapsed into the transmitted path or the reflected path. So if the photon, if the bomb kind of measures the photon to be in the bottom path, then the bomb will explode. But the other possibility is that the photon is instead measured to be at the top path, and then it can carry on. And when it reaches the second beam splitter, it actually splits equally because it doesn't have itself to interfere with here anymore. So it enters a superposition of being reflected and transmitted. So there's some chance that we get it at this detector again, the one on the right, which wouldn't tell us anything because it would be the same as when there was no bomb. But we have some chance of having the bomb be detected with this detector at the top. So this can only happen if a bomb is there. So this is a kind of amazing technique because it allows us to know that the bomb was there. I don't know why I've missed it from this slide, but the bomb should still be here. It allows us to know that the bomb was there without having exploded the bomb, and like with nothing having interacted with the bomb. So that's quite, a crazy application of quantum mechanics. And this has been kind of experimentally tested for, well, not using bombs, but using other systems, like using an atom instead of a bomb that can be in two states. And it's been shown that it's possible to do this. And it's, in this case, we've only got like a 25% chance of detecting this bomb without it exploding, because half the time we'll explode the bomb and another quarter of the time we'll get it in this detector where we don't know whether the bomb was there or not. But a quarter of the time we'll successfully know the bomb was there without having exploded. But setups were later proposed, which I talk about a bit in my video, where you can get this up to 100%, up to 100% effective bomb tester, essentially by using lots of these beam splitters. So why do some people think it's a paradox? Well, some people think it's a paradox because when they look at this situation where the bomb didn't explode and we kind of measured it without interacting with it, they think, well, that's impossible. You can't get information about something without having interacted with it. And so it must be the case that the photon did interact with the bomb and cause it to explode, but it was in another quantum branch, and we must be in a superposition of being in this branch where we've seen that the bomb hasn't exploded and we've worked out that it's there, and we must be in a superposition with this other branch where the bomb has exploded. So this is what Weidmann, one of the people that proposed the thought experiment thinks, but other people strongly disagree and think that there isn't a problem with being able to do this measurement of the bomb without interacting with it. And now people are trying to build various technologies based on this interaction-free measurement. Like there's counterfactual quantum computing, where you can get the outcome of a quantum computing experiment algorithm without running the quantum computer, by kind of collapsing into a state where the algorithm didn't run. And there's attempts to create counterfactual quantum communication, where you can communicate without sending physical particles, and trying to do imaging as well, where you can image an object, like a delicate object like a cell, without allowing photons to actually interact with it and cause damage. So that's why some people think that it could be a solution to Schrödinger's cat in a way, but other people don't. So the answer to this is that the answers to these questions are still controversial, and it depends who you ask. So just to summarize, thought experiments have been instrumental in the history of science, right from ancient times to today. There are people using thought experiments in research today. And they help us imagine new technologies and understand the unusual aspects of quantum mechanics, and trying to resolve the apparent paradoxes that appear when we think about thought experiments, help us make progress in quantum mechanics, and also in they'll help with whatever comes next. So there are thought experiments to test quantum gravity, for example, which is a theory that hasn't been developed yet, and people are trying to develop those theories, which will be like the next thing after quantum theory. And if you kind of want to read about more quantum information things, quantum information, the Oxford Quantum Information Society has lots of past events that are recorded on YouTube that you might want to check out. There's the Qiskit textbook and YouTube channel, which are good for getting an introduction to quantum computing and getting the kind of quantum information background on that. It kind of explains what background you need to get started as well. There's this cool quantum computing for the very curious, kind of interactive online article for learning about quantum computing. There's this quantum flytrap virtual lab where you can essentially kind of play with photons and build quantum technologies in this virtual lab space. There's an Introduction to Quantum Information course available freely online that Arthur Eckert, who is one of my supervisors here at Oxford, has made freely available online. And I've just put some of the popular science books that I've enjoyed on the foundations of quantum information by these are all people working in my group at Oxford. I found The Science of Canon Kant, The Fabric of Reality, and Decoding Reality are all fun to read about the fundamentals of quantum physics. So thanks for listening, and I'm happy to take any more questions that people have.
Yes, that was an exhilarating session. Not everyone can explain the way you did. So thank you for explaining all of these so properly and so well. So obviously we have a lot of questions from the audience for you. So one of them asked that, is this cat experiment valid when the setup approaches the speed of light?
When the setup approaches the speed of light. So, I guess experiment kind of so yes, I'm trying to understand what the question means. Does it mean like if we sent the cat to stop moving at the speed of light or close to the speed of light, then I mean everything should work the same way in that it should become kind of quantum entangled with, well, if you can describe the cat by quantum mechanics, then it can become quantum entangled with the decaying substance. If you have an interpretation where you think it collapses, it should still collapse. But yeah, I'm not sure if there's anything that would be different if it was going at really fast speeds.
Okay, thank you. So we'll move on to the next question. Is quantum, at present, what are the opportunities available to a quantum information and computing undergraduate in the industry as well as in academia?
Mm-hmm. Yeah, there's lots of opportunities available. So as an undergraduate, IBM Quantum and Qiskit, they run lots of kind of education themed and community themed events and initiatives. So if you're interested in quantum computing, for example, then you can kind of learn if you're interested in the quantum software side, then you can learn about using Qiskit, and there are things like the Qiskit advocate scheme, where if you've made some contributions to the community, then you can kind of become a bit more involved in helping with that. So that's something that some people like to do in their spare time. There's also, you could look into kind of doing an internship at a quantum software company or quantum hardware company, or a research placement with an academic institution. So there's lots of research being done on all the different types of aspects of quantum mechanics. So I guess the first thing to do would be to do a bit of research on the different types of research happening, and then think about what you'd like the most, and then start reaching out to people to arrange a call, or to try and have a discussion to find out a bit about what they do and what opportunities might be available to work with them. So I guess I'd recommend kind of following up on the areas that you're particularly interested in, and try and find out kind of who are the main groups doing research in that area, who are the companies working on that area, and then try and kind of contact people at those companies or in those academic institutions to find out more about how to, what opportunities are available. And in terms of kind of future careers, people in the quantum industry are really looking for a complete range of backgrounds, like physics, computer science, maths, chemistry, biochemistry, biology. I think engineering, all these STEM backgrounds have really, maths as well. People are looking for people from a range of backgrounds. And there are some roles where it's useful to have a PhD to do, but there are some companies that are happy to take people without a PhD as well. So you could consider whether you'd want to go down that route as well.
Okay, I see. Thank you. So there's a lot of curiosity surrounding your work on quantum Minesweeper. So can you elaborate a bit on that?
Mm-hmm. Yeah. So the quantum Minesweeper idea was, if I have one of the pictures I showed right at the start, showed a quantum circuit. So essentially, in the quantum Minesweeper video, I explained the quantum bomb tester thought experiment, and then I explained how I've turned it into a quantum circuit, which then I can code on a quantum computer using Qiskit. So the idea there is that so as I mentioned before, quantum computers are based on qubits, and you can apply quantum gates to these qubits. That's how you program quantum computers. What I did for the quantum Minesweeper video is essentially take this experiment that people think of in terms of photons and this setup of the bomb tester, and I kind of abstracted it away to like, well, what's actually happening if you write everything out in terms of just qubits. And when you kind of abstract it all to that level, then you can see kind of what quantum gates these different parts of the circuit correspond to. So the beam splitter, for example, which puts the photon from one path into a superposition of two paths, I represented that by a Hadamard gate, which is a quantum gate that you can apply to a qubit, which puts the qubit from a 0 state into a superposition of 0 and 1. So I kind of drew those kind of analogies between the physical bomb tester setup and the more abstract qubits to create a quantum circuit. And this here is the quantum circuit that I turned it into. So this is the Hadamard gate. A controlled NOT gate represents the bomb measurement. Then another Hadamard gate is the second beam splitter, and then measurements of these qubits. And so the way this kind of turned into a game of quantum Minesweeper is that essentially by measuring the qubit, you can find out whether to predict that the bomb is there or is not there, and then you can play that as a game on the quantum computer. So it's a bit, implementing it on a quantum computer is a bit different to doing it in with like the photon setup that I described with the beam splitters, because in that setup, like, you actually aren't interacting with that bomb at all, whereas in the quantum computer setup, you've actually got all these qubits interconnected. So it's like a different physical setup, but it's described by the same quantum circuit. And so this quantum circuit is the same for the bomb tester I described in this presentation as well, and for the circuit that I then run on the IBM quantum computer.
Okay, great. So there's someone in the audience who is currently a computer science undergraduate, and he attended the Quantum Global Summer School in 2021, and also the Q-World's Q course, and is quite interested in quantum computing. So his question is that how should he start building his career in quantum computing?
Mm-hmm. Cool. Well, it sounds like those activities are definitely a good start. I guess, an internship is a really good way forward. And any research experience, I guess, making, if it interests you as a computer scientist, kind of making contributions to the Qiskit community if you can. I guess, different people have different things they want to focus on. So for me, I like the kind of communication aspect of things and organizing events and things. So that's led to my involvement in the quantum computing area being focused on kind of making videos and organizing events and things. But for other people, it might be that they're focused on, say, contributing to code on quantum software, or it might be to do research on quantum hardware, or like writing really good tutorials online, or having their own channel of explaining things online, or setting up kind of workshops or events in other communities or targeted at other people. So there's a kind of huge range of things that you can do in the quantum space. So yeah, I think it's a matter of finding out what kind of you want to focus on, and yeah, internships, research placements, and I guess courses, if there are, like there's the online courses that I mentioned, you can use them to learn more, or yeah, if there's other courses that you're involved in or that are offered at the university or around, then taking them. And I guess networking with people that are interested in similar things as well. So attending events, talking to people, and yeah, then you can kind of hear about different people's experiences and keep an eye out for opportunities for collaborations or working with other people as well.
Okay, thank you. So with that, we have come to the end of the question answer session. We heartily thank you for giving us your time and deep insights. So we wish you all the best for your future endeavors. And it was a really great and enlightening session for all of us. I'm sure all of us enjoyed it.
Great, thanks a lot.
Thank you so much.
Okay, thanks. I'll see you then. Thanks again for inviting me.
Thank you, ma'am.
Thank you.
Yeah.
Thank you very much.
Thank you, ma'am.
Thank you so much. Bye.
Thank you, ma'am.
Thank you.